Fine. Fine. See, now we are discussing about thermal expansion chapter. Before that, we will have a brief discussion about um, what you call scale of temperatures. See, the entire heat chapter lasts for 4 weeks. First week, thermal expansion calorimetry. Second week, it is kinetic theory of gases. Third week is thermodynamics. Fourth week is transmission of heat. So in all these areas, we will repeatedly use one thing called temperature. What exactly is temperature? That is the first question that we need to ask ourselves. What exactly is temperature? Before that, I would like to confirm you when I am speaking about heat refers to what? Heat refers to a form of energy inflow. Remember, when you say heat, it is the energy only when there is it's transferred from one body to one another body. What is the criteria for transfer of heat? Compulsorily, one body must be hot, the other body must be cold. That is the compulsion for you. But how to discriminate hot or cold? We require some reference. When I say 0 degrees centigrade, don't feel that that is the lowest. For example, in Russia, some countries, the normal average temperatures there of the order of sub-zero, -50, -40 also. In polar regions, there are some places where temperatures are of the order of -100 also. When compared to -100 degrees centigrade, 0 degrees centigrade is a better height. So temperature refers to relative degree of hotness or coldness. It is a relative. So therefore, one more important point is when I say thermal equilibrium, for example, when I say thermal equilibrium, I say that two bodies are in thermal equilibrium under only one condition. I don't see any transfer of heat between them. Net transfer of heat between them. Point number two, they both the bodies must be the same temperature. It is not that, for example, you take a lead shot, small lead shot, heated almost close to its melting point, and you drop it in a container containing water. See, after some time, what you will notice is that the lead shot and the water remains at the same temperature. See, don't speak about the heat in lead or heat in water. Wrong. We will correct that when we deal thermodynamics chapter. See, temperature never inform you that this body is having that much amount of heat. I said relative hotness or coldness. That's all. So, in thermal equilibrium, temperature is the property that remains the same Temperature is the property that remains the same when two bodies are in thermal equilibrium. When two bodies are in thermal equilibrium. Okay, that is the introduction to temperature. See, please note that temperature, is one of the fundamental quantities what we have. One of the fundamental quantities what we have. Remember, it's SI system, unit is Kelvin. Temperature is basically a scalar quantity. When you give heat to a body, its temperature rises. If a body loses heat, you will see a drop in the temperature. That's it. So for this purpose, we require some scales, scale of temperature. I repeat, scale of temperature. Basically, we deal with only three types of thermometers. See, when I'm speaking about scale of temperature, on the basis of some property, we will design thermometers. Okay, the instrument which measures the temperature of a body is what we will call a thermometer. Instrument to measure temperature. Right. Now, any thermometer, this works on some property. Like I'll discuss it later once I introduce the scale, the three different types of thermometers. See, you will have three different types of thermometers. One is the famous which we know. One is Celsius scale. The other is Fahrenheit. The other is Kelvin scale. See, every thermometer will have a lower fixing point and upper fixing point. Usually, freezing point of water and boiling point of water is taken as references for these definitions. Okay, you can write this: a freezing point of water and boiling point of water. So in Celsius scale, that is taken as 0 degrees centigrade, and this is taken as 100 degrees centigrade, and this gap is divided into 100 equal division. Whereas in Fahrenheit thermometer, this is taken as 32 degrees Fahrenheit, and the upper is taken as 212 Fahrenheit. 212 degrees Fahrenheit. Kelvin scale, this is 273 Kelvin. Kelvin ki degrees pettakoodaru. And this is 373 Kelvin. Kelvin scale is actually modern. And the Kelvin scale is what we will call as it's a thermodynamic scale. thermodynamic scale. Kelvin. See, for normal thermometers, actually you require two reference points like Celsius, Fahrenheit. There is another Romer scale that is also there, whose what do you call lower fixing point is 0, upper fixing point is 80. It is also there. But only Kelvin depends only on one point, not on two different points. Kelvin is scaled, the zero of that scale is it is defined properly. And what do you call, this is on the basis of triple point of water, whereas you don't require two reference points. You just require to measure some property at triple point. Okay, so this is how you define a thermometer scale. So in general, if I wish to construct any thermometer, now I have understood that the thermometer is to be constructed mostly in the linear way, such that reading on any scale minus in that scale lower fixing point by upper fixing point minus lower fixing point must be constant. You design any thermometer. Tomorrow, Pavans are thermometer. So in that reading, some 32 peak minus lower fixing point by the upper fixing point minus lower fixing point must remain constant. Because all these things are constructed on the basis of some properties, some basic properties, right? So in general, to generalize this, I have one more centigrade minus 0 by 100 minus 0 is equal to T Fahrenheit minus 32 by 212 is T Kelvin minus, actually it is 273.15 by 373.15 minus 273.15 is your temperature minus lower fixing point by upper fixing point minus lower fixing point. That is how you will decide right. That is how we design any thermometer. Okay. So in modern thermometer, you will use this technique, only one fixed point. Whereas the old thermometers, they require two fixed points, lower fixed, upper fixed. So in general, the relation between these three scales, just I am taking straight away. So we want relation between Celsius scale, Fahrenheit scale, and Kelvin scale. In general, is decided as Tc by 100 is equal to Tf minus 32 by 180 is equal to T carrier 0.15. This is 100. Or in other words, 5, 9 correct है ना? 5 temperature scales. That's the deal. So in general, basically we require relation for Fahrenheit and centigrade regularly. So therefore, T Fahrenheit is 9 by 5 times T centigrade plus 32. Right. మధ్య మధ్యలో చెక్ చేస్తూ ఉండాలి రికార్డ్ అవుతుంది. Right. So that's the basic relation. See, again I am telling, we will design thermometer on the basis of some physical property that changes with the temperature. For example, it can be length of liquid in capillary tube, your mercury thermometer. Pressure change at constant volume. Volume change at constant pressure. A resistance of a platinum wire. Now, these are the different, I'm just giving you some examples, that's all. These are some examples. Like I'll explain. Call me within that. Right. No. Imagine property X, taken temperature along some x-axis. A property Y instead of X, because there might be some confusion for you. I know two informations on this. At some temperature T1, I know the property is Y1 and it changes linearly. Similarly, at some T2, property is Y2. So I want to measure T when the property is Y. Because in all the cases, I have taken linear variations. Can you please help me in forming an equation here? Can you please help me in forming an equation here? What is the equation? Y2 minus Y1 by T2 minus T1 is Y minus Y1 by T minus T1. So Y2 minus Y, 1 minute. Y minus Y1 by Y2 minus Y1 is T minus T1 by T2 minus T1. It is nothing but temperature in that scale minus lower fixing point by upper fixing point minus lower fixing point is a constant. Can you please tell me why it is a constant? You take any scale, property is remaining the same. Property, say for example, variation of length, variation of resistance remains the same. Any doubt till this point? boys and girls? Any doubt till this point? But this is all old methods. In modern thermometry, in modern thermometry, ah, instead of two fixing points, okay, we will choose only one reference point. And what is that reference point? Triple point of water. So therefore, in that case, temperature in Kelvin is 273.15, means in that case simply allow at that temperature the property is XTR or YTR. So you want some temperature to be found, T Kelvin. I'll simply find Y at that temperature. Geometry says T Kelvin is 273.16 times Y at that temperature by Y triple point. Just you need to measure the property at triple point. You will get everything. Triple point is that temperature where all the three states of matter coexist. Water, water vapor, and ice. It is possible at 273.16 and very low pressures. Not the pressures which we are discussing here. Low pressures. We have that triple point concept. I'll discuss that anyway in the class. Right. These are all just some basics, very simple basics. Right. Just I've introduced earlier, there are different thermometers. We will use the thermometers which we will use are one liquid thermometer, okay, gas thermometer, resistance thermometer, thermocouple thermometer, magnetic thermometer, vapor pressure thermometer. See, first three are linear, the other three are non-linear. Each one have their own purpose. If possible, we will discuss at a later stage, but I'm just introducing this. Okay, remember, I'll just take some reference on this. See, See, liquid thermometer is on the basis of thermal expansion of the liquid. Gas thermometer, Charles on the basis of Charles P proportional to T or V proportional to T. Resistance thermometer, on heating the temperature changes. So that you will call as resistance thermometer. Thermocouple, it's something totally different. It's totally different. Different in the sense uh, you will make two junctions by the combination of two wires, say like for example iron and copper. One junction is maintained at cold ice blocks, the other hot, whose temperature is to be measured. An EMF is generated. On the basis of the EMF generated, you can measure the temperature. Magnetic thermometer, susceptibility is inversely proportional to temperature. On that, Curie's law. It works on Curie's law. Vapor pressure, it works on the some basic principle of saturated vapor pressure, which is over period of time you will learn. Just introduced the nature. Someone was asking me triple point. I am just mentioning again. For water, 273.15 Kelvin temperature and a pressure 4.5 mm of mercury. You know what is a normal atmospheric pressure? When compared to 76 mm of Hg, అంతే కదా. Okay, what when converted into mm? 760 mm of Hg. When compared to 760 mm of Hg, what is 4.5 mm of Hg? Very low pressure. So under such conditions, matter exists in solid, liquid, vapor together. Such a point is called triple point. For water, I have written here. Right. I think that is fine. We will go for thermal expansion. Whatever it is required for what you call scales of temperatures, I have done. So let us study the reason for thermal expansion. Why there is thermal expansion, right? Are you late go acha? Right. Next. What is the basic reason for thermal expansion? See, what is happening when matter is heated, that we will study. When you heat matter, first you will see two things, a rise of temperature. Also, you will see thermal expansion too. The object dimensions will change, increase. Right. Why it is happening? Let us study. You already know in solids there exists a force of attraction between two atoms, two molecules in it. Now you plot potential energy as a function of distance graph, you will get the graph like this. So what? There is asymmetry in the graph. Means what is this? That is the potential energy of the system at 0 Kelvin, for example, where almost the motion stops, the motion ceases. Now you gradually heat it, the content. T1 stands for a different temperature. T2 a next higher temperature. T3 next higher temperature. So what is that happening? The moment when you start heating, it's oscillating. Undoubtedly, at a time, this is the minimum distance of separation. This is the maximum distance of separation in the process of oscillation, and the average distance of separation. What's happening now? Is it R naught or more than R naught? More than R. Huh? Because of the asymmetry, not symmetric. The graph is not symmetric. అందుకే SHM లో కూడా మనం వాట్ ఈస్ సింపుల్ SHM లో సింపుల్ అంటే వై ఇట్ ఈస్ సింపుల్ బికాస్ సిమెట్రిక్ లెఫ్ట్ సైడ్ whatever the amplitude you see, right side also same amplitude is. Whereas in solids the heating process takes place like this. So because of the asymmetry, because of the asymmetry in oscillation, you will see that as I heat gradually, the average distance of separation keeps increasing. What exactly that refers to? Yes, average distance of separation gradually increases. You will see an increment in the size of the object. So this is the fundamental reason for expansion of matter on heating. Suppose if it is not asymmetric, what happens? The average distance of separation remains the same at any temperature. So you will not notice any expansion, right? So therefore, so what is my point of conclusion here is this is the line. So thermal expansion out of all the three forms of matter, least in atoms, sorry, solids, because the atoms and molecules are strongly bound. High in case of gases, right? Solids will have three types of expansion. Solids expansion can be classified into three types. Linear expansion, which is in one dimension, superficial expansion, which is in two dimension, and volume expansion, which is in three dimension. Here we are dealing with isotropic materials only. Right. Now, while I am dealing this, we require some more information, or we need to learn something more related to this. Right. So thermal expansion in solid is basically classified into three categories. One, linear, lengthwise, superficial, area-wise, volume. Okay, you know already. But for an isotropic material, you don't require to study all the three, right? For example, I am taking only linear expansion right now. I am assuming that yet some temperature T naught, that's the length of the rod, which I will call this one as some L naught. Slightly heating, slightly. So that the temperature now becomes T naught plus delta T. What happens? You will notice, see, reference ke rasta. It doesn't mean that expansion happens only in the right side. Expansion happily equally, but to notice the change, I am writing one end as a reference. Now this is no longer L naught. In fact, this is L naught plus delta L. Got the point? Now I will heat it further to delta T. To my surprise, I can notice that it is L naught plus 2 delta L. So I have understood one thing. The increase in the length is proportional to rise in temperature, not the temperature. Not only that, the increase in length is proportional to the initial length. You give same rise to 1 meter steel rod, same cross section, 1.5 meter steel rod, same cross section. Go for the same rise. You will notice the increase in length is high for 1.5 meter steel rod when compared to 1 meter steel rod. Therefore, out of this, the increase in length is some constant alpha times L naught delta T. This constant of proportionality is called, we will actually call this as coefficient of linear expansion. Its units are degree centigrade inverse or Kelvin inverse. See, coefficient of linear expansion depends on three things. One, nature of the material. Two, it depends on scale of temperature also. So because same thing will have a different values in different scales. Because 1 degree difference in centigrade is not same as 1 degree difference in Fahrenheit. Because of this reason, it also depends on the scale which you are using. So therefore, finally I can write the length finally can be written as L naught times 1 plus alpha delta T. Remember, honestly speaking, this is not correct. For a large changes of temperature, you cannot use this. This is applicable only for small changes of temperature. And also, in this case, you are using it for length, expansion. You can use the same relation for contraction also, because on cooling, it contracts. On heating, it expands. Right. So, therefore, average alpha is defined simply as delta T. Okay. So alpha, sometimes it might change element to element. Even for some materials which are not isotopic, alpha might change. Depends on where you are likewise. But in this case, I have seriously chosen what? Isotropic material. Right. ఇది చెప్తానికే చికాకు ఉంది, మళ్ళీ అది కూడా ఎందుకు మనకి, రైట్. నెక్స్ట్, సిమిలర్లీ what I have dealt right now is a linear expansion, superficial expansion, what you have is same. We will represent this with the beta. Beta is simply delta A by A naught times delta T, or A is A naught times 1 plus beta delta T. Again, the same terms. Beta depends on nature of the material and beta depends on the scale of temperature. Next, volume expansion. Volume or cubical expansion. This we will represent as gamma delta V by V naught delta T, or simply V is V naught times 1 plus gamma delta T. Any doubt till this point? Pakka? Sure? Right. Now we will try to understand. See, this is all for solids only. This is all for solids only. Now you take a cube. Now you take a cube whose initial dimensions are 1 unit, which is say at 0 degrees centigrade. Now you have expanded this cube what happens, because initially it is 1 meter. Now I have raised this to 1 degree centigrade. Can you please help me in writing the side right now? Isotropic material means dimension, expansion is equal in all directions. So what should be the what should be the length? 1 plus alpha. Now what is the final area? 1 plus alpha square. What is the final volume? 1 plus alpha whole cube. What is the initial area? 1. What is the initial volume? 1. So what is beta? Change in area by initial area into rise in temperature. What is change in area? 1 plus alpha square can be written as 1 plus 2 alpha, because alpha is of the order of 10 power minus 6. Alpha square is very, very small. So you can nearly write this as 1 plus 2 alpha minus 1 by 1. So beta is 2 alpha. Remember, you are not allowed to use this for whatever the material is, only for isotropic material. Next, in this case, gamma is delta V by V naught delta T. Delta V is 1 plus 3 alpha minus 1 by 1. This is nothing but 3 alpha. Gamma is 3 alpha. So finally, alpha is to beta is to gamma is 1 is to 2 is to 3. Remember, this is for isotropic material. Only allowed for isotropic material, not allowed for some other material. For example, if some other material is having different, say, alpha x, alpha y, and alpha z in 3 different dimensions, beta is written as alpha x plus alpha y plus alpha z in that case. That will approximately. But basically, we will deal with isotropic materials. So I have just introduced thermal expansion part for some solid, right? So yeah, well, we will deal some properties related to thermal expansion. One such property is that uh, thermal stress, that I will discuss right now. And there is another property which is called bimetallic strip. That also I'll discuss. నీ పాఠం చెప్తూ ఉంటే వెళ్ళు. Right. This topic just requires some diagrams and all that. So I'll use this. Okay, no issues that I need to. So now you can see you have two strips of equal lengths. You will use this arrangement wherever temperature control is required. You will use this in this system in iron box. You will use this system in what you call in AC. You will use this in your refrigerators also. See, two strips of equal lengths but of different materials. You can see that one material here is made of steel, the other material is made of brass, right? When they joined together, the combined strip is called a bimetal. Name itself is reflecting what it wants to express and can be used in thermostat. The functioning name is called thermostat to break or make electrical contact. See, when you want certain temperature is reached, then you don't want to heat further. what happens? That temperature is to be maintained as a maximum. You will use the thermostat. Why? I will explain. When you heat, what happens? See here, alpha of brass is greater than alpha of steel. So naturally, brass expands more than steel naturally. But because of the issue here, what is that? Combined. So it will bend. Which side it will bend? The one with more alpha will be on the convex side. So now, for example, for a circuit, this is how it is in contact. Once heated, it disconnects from the contact. Say like for example, like this. Now a gap is maintained. Disconnected means no current passing through that point now. So therefore, what will happen? That temperature is maintained in the unit. Thereafter, what happens? Tell me. It will cool down naturally. Automatically, this will take the original form. Again, contact is maintained. Again, current flows. Again, heating. Once that temperature is reached, it will bend. This is the working principle of thermostat. So, on the other hand, if it is cooled, what happens? You see, on heating, it's clearly mentioned here. On heating, the strip will bend with the metal of greater alpha on outer side, convex side. On cooling, the metal with the greater alpha lies on concave side. That's the principle upon which a bimetallic strip is used. Next, different applications are there related to this. Let me take up the first application, and that application is the effect of time period. One observation is that difference of length remains a constant. Now you have a rod whose length is L1 made of material alpha 1. You have another rod made of material alpha 2, length L2. You want the difference between these two remain constant at all temperature due to some reasons. Reasons I'll describe later. Now, for example, I am just heating it to some temperature T. So, L1 dash is L1 times 1 plus alpha 1 T. L2 dash is L2 times 1 plus alpha T2. What condition you want is always. Now, can you please help me in writing L2 dash minus L1 dash? L2 dash minus L1 dash, which is nothing but L2 minus L1 plus L2 alpha 2 minus L1 alpha 1 T is L2 minus L1. Therefore, L2 alpha 2 is L1 alpha 1. If this condition is satisfied, the difference of the lengths remains constant all the time. All the time. Okay. Next. Uh, Next aspect is effect of temperature on the time period of a pendulum. All these things you would have gone through long time back in your schooling and all that, but just it's a fundamental basic class discuss. We already know the time period of oscillation of a pendulum is given by 2 pi root L by G, which means T square, or in other words, L proportional to T square. Rest of the terms are not affected with temperature. For small changes, delta L by L can be written as half delta T by T. Till this point, any doubt? Okay. Right. So we are worried about the right hand part, actually. So delta T by T is I think 1 minute correction here required. So delta T by T is half alpha delta theta. Now because too much of times these terms are involved, to avoid temperature, I'm using theta now. Right. So delta T is half T alpha delta theta. Otherwise, I can write simply T is T naught into 1 plus half delta theta. So which clearly implies the time period gets affected because of, right. Now, for example, my pendulum clock shows correct time at T naught degree centigrade, for example. T naught degree centigrade. T naught degree centigrade, for example. This is a problem with recording class. T naught degree centigrade. Now, there are two possibilities. One possibility is, what is that? One possibility is the temperature may fall below T naught, T low, T high. Now, in this case, what happens? As the temperature drops, what happens? No, hold on, sir. Stay cool first. Length decreases, right? Time period decreases, clock runs faster. Or clock gains time. So now in this case, what is happening is per day. See, when you are calculating delta T by T, I know this is a half alpha delta theta, which is half alpha modulus of uh, uh, TL minus T naught. I know. So per day, gain in time is half alpha T naught minus TL times 86,400, because per second, that is the variation. When you write delta T by T per second, per day, when I am writing, in a day, you will literally gain half. That is not a big time. Actually, one more point. Throughout the day, temperature won't be TL. But if you take throughout the day, it is a TL. Even then, alpha has some term 10 power minus 6. So hardly few seconds or even less than a second, you will have correction. Otherwise also, if in this case, clock runs slow or clock lose time. So delta T by T is half alpha, delta theta is half alpha T high minus a T naught. So similarly here also, per day loss in time is equal to same half alpha into T naught minus T1. 1 minute. No, space is the criteria. Same, but loss per day. That's how we'll write loss per day. Because it is all due to thermal expansion. Next, error in measuring length. Length correction. Remember, your scale is here. 0 degree 0 and 100 centimeters. And this is calibrated at a T naught degrees centigrade. And I am measuring a wooden block. Why I took wood? Because it won't get affected because of thermal effects. Now exactly, it's now showing some 80 centimeters. Now I'll take up the same arrangement at different temperatures. The scale 0 will be fixed here only. I will heat. On heating, the scale expands. Your 100 centimeters will now somewhere over here. Wood remains the same, but the reading here will now be your 80 centimeter mark is somewhere over here. You are measuring a lesser length. You require some correction. You badly require some correction. Why? You may, because of the expansion of the scale. So therefore, correct length is measured length plus L alpha delta T. That's the correction. On increasing temperature, you should do positive correction. Because, explain the reason there. Suppose if the scale contracts, it will show 100 centimeters at a lesser side. your wooden stick still remains the same. But now the reading shows 80 centimeters here because of the contraction. Now again, correct length is equal to L minus L alpha delta T. Remember, calibration is done at T naught. At a lesser temperature, negative correction. At a higher temperature, positive correction. Okay? Any doubt till this point?
In that formula, Arnold's is supposed to be different. It's different in the
L very.
already similar.
Uh,
The L plus L dash alpha.
అక్కడ L same.
Same.
Alpha delta T is correction actually per unit length.
L alpha delta T the expansion of the L part and the measured length part.
Measured length. Whatever the measured length you will have, it actually binomial theorem parts are correct. Is okay, fine, that's okay.
Measured length expanded part is one can order. అప్పుడు దాన్ని యాడ్ చేసి ఏం చేస్తుంది
పర్ డిగ్రీ ఎంత అయిందనేది చూసి పర్ సెంటీమీటర్ ఎంత కరెక్షన్ చేయాలో చూసి చేసాం అన్నమాట. You measured this much per centimeter, correction is alpha delta T for suppose. Per centimeter కే కదా కరెక్షన్ వేసేది.
అక్కడ యూనిఫామ్ ఉండదు కదా ఇక్కడ ఎక్స్పాన్షన్ తక్కువ ఉంటుంది అక్కడ
ఎక్కడ ఉంటుందంట?
ఇక్కడ స్టార్టింగ్ లో
The entire scale at T naught, the length of one division is 1 centimeter. Now what is the length of 1 centimeter? 1 centimeter on the scale.
Okay.
It is no longer 1 centimeter.
Alpha delta T.
Right. The next part.
Should have put in rod if we have a rod, then it will be acting like a bimetric structure.
Why I should take brass rod? What is my discussion here? Please tell me. How to correct it is what I am doing. You are doing something else which is not required here. See, with respect to some standard length, how you will correct. That's what. Okay? Right. Next. ఇంకా now what I'll deal with thermal stress. See, you have two rigid walls like this. You have two rigid walls like this. And at some temperature T naught, length is L, made of material alpha. Now you are heating this. Honestly, what is that you will expect is the rod need to take a length this much. But you are not allowing the rod, to expand that much. What is initial length? L. What is final length? L plus L alpha delta T. But in our case, what is the final length? L. So what is strain in this? That is strain. Strain units and all. Right. What is stress? Young's modulus times strain. Y alpha delta T. And this is called thermal stress. You will see this stress in the rod. అందుకని మనం వేసేటప్పుడు ఏం చేస్తామంటే when we are laying railway tracks, you will leave small gaps. If that gap is not allowed, what will happen is because of the thermal stress, it will undergo bending, it will undergo change in shape. So to avoid that, we will leave gaps. Even bridges also, we won't connect both ends to the pillars. One end is rigidly fixed to the pillar, the other end is left free on a roller, which supports the expansion of the bridge. Because basically you are using concrete and all that in that case. So some basic areas that what I wish to do, I have done basically. Error in the correction, right? Solve its purpose. Now we will step into numericals. Numericals. Ah, where is the delta L, man? Yes, this is the change.
But it's not happening.
That is the reason why stress is developed. It was maintained L, which was supposed to be L alpha delta T extra. But L alpha delta T is taken as a compression in this case. Because there is a compression, there is a stress. ఆ కేసు నేను ఎందుకు చెప్తాను అప్పుడు ఒకవేళ అయింది, వాట్ ఈస్ ఆఫ్ యూస్ ఫర్ బెండ్ అవ్వదు, వెయిట్ నెగ్లిజిబుల్ అని తీసుకుంటాం. రైట్, నౌ లెట్ us స్టార్ట్ డూయింగ్ న్యూమరికల్స్ one after the other. I start with this 1.4. See, he is madly running at time. Right. Brass rod of length 50 centimeters, diameter 3 centimeters is joined to a steel rod of same length and diameter. What is the change in the length of the combined rod at 250 degrees centigrade? So very simple. Delta L brass is alpha brass, L brass, delta T. Delta L steel, alpha steel, L steel, delta T. They are free ends. They are not rigidly pivoted or something. Free. So the total delta L is delta LS plus delta LB. Alpha S LS plus alpha B LB delta T. Just substitute, you will get the required answer. See, in this case, note that it is the combination is free to expand. Free to expand. So therefore, in this case, no stress. Yeah, obviously. You are not locking now, free ends. Right. Actually, more deeper cases we will deal later. I mean, next class. I think. Right. So, free to expand, there is no stress. So, by doing which, you will get answer as 0.34 centimeters. So, I'm giving you the concept and leaving. Go for the next question. You have an isosceles triangle formed with a thin rod of length L1 and coefficient of linear expansion alpha 1 as the base. Right. Let me first draw the diagram. What do you want? This is L2 alpha 2. L2 alpha 2, L1 alpha 1. If the distance between apex and the midpoint of the base remains unchanged, which means H remains a constant. What is the condition? That's what you want. నాకు ఇదంతా తెలియదబ్బా మ్యాథమెటిక్సే వాడుకుంటాను హెచ్ స్క్వేర్ ప్లస్ L2 square is L1 square by 4 is L2 square. Yes, any doubt?
Sir, it's not right angle triangle. Okay, right angle.
For your midpoint,
Like isosceles.
H square plus L1 square by 4 is L2 square. Differentiation 0, 2L1 by 4 delta L1, 2L2 delta L2. 2 cancel. L1 by 4 times L1 alpha 1 delta theta is equal to L2 times L2 alpha 2 delta theta. Any doubts? So finally, L1 square alpha 1 is 4L2 square alpha 2. So L1 by L2 is 2 times root alpha 2 by alpha 1. Right? Sure. Next. Any doubts? Please ask. I didn't do anything magic here. Whatever the question that they asked, I responded accordingly. Any doubts? Next. A metal rod A of length 25 centimeters expands by 0.05 centimeter when its temperature is raised from 0 to 100. Okay, fine. You have another rod B of different metal whose length 40 centimeter expands by 0.04 centimeter for the same rise in temperature. God. A third rod C of length 50 centimeters made up of two pieces of A and B together to expands by 0.03 centimeter on heating it from 0 degrees centigrade to 50 degrees centigrade. Find the length of each. No, see, there is some data that you need to take up. The first part of the data is alpha A is delta L by L alpha delta T. Delta LA by LA times delta T. Right. 0.05 by 25 times 100. Can you please help me with this value? I think it is 2 into 10 power minus 5 vega. Agreed? Alpha A, alpha B, delta LB by LB delta T, delta LB 0.04 by 50 I is the length. 1 into 10 power minus 5 degrees centigrade. Right. See, I am assuming that in the construction of the rod, C, L1 portion, I am using material A. L2 portion, I am using material B. Right. So what is the delta L of this part? Delta L1 plus delta L2. And remember, you have given me delta L, which is 0.03 centimeters. delta L1, no idea. But what I can write is L1 alpha A delta T plus L2 alpha B delta T. Oh, hold on. See, hold on. L1 alpha A 2 plus L2 alpha B is area delta T contains 50 100 by 2 10 power minus 3 by 2 2 into 3 into 10 power minus 2 into 10 power 3 ఇదెంత వస్తుందరా 60 centimeters 2L1 plus L2 60 centimeters L1 plus L2 50 centimeters. So difference వచ్చేసి L1 is equal to 5 centimeters. కరెక్టేనా? 10 centimeters. L1 10, L2 40. Okay? Oh. ఏదన్నా లేరా ఈ చాప్టర్ అంతా అదే రాస్తాం లేకపోతే వాడు ఇస్తాడు డాడ్ ఆల్ఫా యాజ్ ఎ ఫంక్షన్ ఆఫ్ టెంపరేచర్ ఇస్తాడు అదర్వైజ్ ఆల్ఫా ఇస్ ట్రీటెడ్ యాజ్ కాన్స్టెంట్
Twice of alpha beta. Expansion in is twice of expansion in B.
Length మీద కూడా depend.
ఇనిషియల్ లెంత్ మీద కూడా డిపెండ్ అవుతుంది రైట్ విల్ డీల్ ఇన్ ద నెక్స్ట్ క్లాస్